Hello students, hope you are doing well. This is Suryam, Assistant Professor, Department of Pharmaceutics, Vishnu Institute of Pharmaceutical Education Research, Narsapur. Today we are here to discuss another most important topic from the colloidal dispersion system, that is electrical properties of the colloids. In this class, we are going to discuss about the electrical properties of the colloids like zeta, potential, and DLVO theory. These are the two concepts which we can consider as the electrical properties of colloidal dispersions. And this colloidal dispersions electrical properties are very important topic. Let us discuss in detail about the zeta potential. The potential difference between the dispersion medium and the stationary layer of fluid attached to dispersed particle is known as zeta potential. Or we have another definition of this zeta potential, that is, it may define as the difference in potential between the surface of shear plane, that is tightly bonded layer, and electroneutral layer, which is also known as loosely bonded layer, is known as zeta potential. This zeta potential is denoted by the Greek letter zeta. Units millivolts. I think there will be some confusion related to this definition of zeta potential, but it is very simple. See, it may define as the difference in the potential between surface of the shear plane, that is tightly bonded layer, and electroneutral layer, that is loosely bonded layer. So here you need to take two layers. This is tightly bonded layer and this is loosely bonded layer. Okay, so in this, the distance difference and potential difference. So what is potential? Potential means the energy. Potential means energy. You can say this zeta potential, the energy differences in between the strongly bonded layer or tightly bonded layer and loosely bonded layer. So what is this tightly bonded layer called as here? Shear plane. And what is the loosely bonded layer called as? Electroneutral layer. So overall conclusion of the zeta potential is that distance in potential in between strongly bonded layer and loosely bonded layer is considered as zeta potential. To understand this zeta potential, let us take a colloidal particle from a colloidal system. So this is a colloidal system. This is the colloidal system. And you don't forget, colloidal system means it should contain dispersion phase and dispersion medium. From this we can take any particle like this, and this particle which is contains negative or positive charges on the surface. So let us consider this particle. This particle means this one. Now this is the, we are taking negative charged particle. This is, let us consider this dispersion phase particle contains negative charged on the surface of the dispersed particles. So what will happens when we have negatively charged particles, and then that negative charged particles will attract positive charged particles. Clear? So this negatively surface area, this is the negative charged particle, and this negative charged particles attracts always positively charged ions or particles, and they get attraction each other and they will form a layer like structure. This layer is known as Stern layer, or also known as, just now we discussed in the definition, that is strong bonded layer, or also known as tightly bonded layer. And after this, so this negative charged particles got attracted with positively charged particles, and now we have positively surface here. This is positive surface. Now what should happen? This positive particle should attract the negative one. Now we will be getting another charged particles, that is negative charged particles, like this on the surface of the Stern layer. So this will be the second layer. So in combination of these two layers, this is known as loosely bonded layer or slipping plane. Next, after this loosely bonded layer, now we have negatively charged, right? And this negative charged particle will try to attract positive charged particles, positively charged particles, like this, and here they will form another layer. And now on this layer we have positively charged ions, and now these positive charged ions will be get attracts with negative charged ions, and this will be continuous like this, positive negative positive negative positive negative. Clear? So what happens? So if this is a center point, this is the center point, and as the distance is increasing from the center point here, as the distance is increases from this strongly bonded layer, and rest of the layers will be considered as loosely bonded layer, because there is no potential is there. Where we have a strongly bonded layer, then we can have more energy, and as we are increasing in the distance by means of the positive molecules are getting attracted with the negative, negative with positive, again positive with negative, again negative with the positive, like that the distance is going to increase. As the distance is increasing, the potential will be decreases. That is what the zeta potential. In the diagram, the particles contains negatively charged on the surface and it will binds with positively charged particle, we discussed that, and forms a strong bonded layer shown in the diagram. Yes, that was shown, and is known as Stern layer or strong bonded layer. After Stern layer or strongly bonded layer, the charges on the surface on the particles associates irregularly and forms loosely bonded layer, which is also known as diffusion layer or electroneutral layer. From the above theory, this can be represented in the graph as follows. Like we need to understand the diagrammatic structure in a graphical manner. For that, we need to take x and y axis. On y axis, we need to consider the charge, because charge, that is negatively charged. In the previous diagram, we consider the dispersed particles which contains negatively charged. If we are considering the particle as positively charged, then here we need to take the positive charge on y-axis. Why we are only taking negative charge here means we consider the dispersed particle which contains negatively charged. That is the reason we are taking this charge on y-axis as negative. On x-axis, we need to take the distance. So now we need to compare what happens as the distance is increasing as charges. Charging means positively charged or negatively charged. Initially, we will get this curve, and this curve is known as surface potential region, and this point is known as Stern potential region. and after that, as the distance is increasing, the potential region will be formed. So you need to remember 3 points here. First one, that is surface potential region. What happened in the surface potential region? We took negatively charged. This charge we took. Okay. So this negative charge particles will attract the positively charged particles, and then they will be form a strongly bonded layer. Here we got a strongly bonded layer, that is known as sternopotential region. This is sternopotential region. And after that, again this positive surface will be attracts with negatively charged particles or negatively charged ions, and this negatively charged particle will attracts with positively charged, like this. And after some time, this positive charge will attracts with negatively charged. So what happens? Slowly the distance is increasing. Slowly you can observe in this graph, the distance is increasing like this. Here the distance is very less comparatively this and this position. So in this position we can form a sternopotential region, that is strongly bonded layer. When from the starting point to ending point, the distance has been increased. Distance is increased. So what will happen? There will be changes in the energy, and that changes in the energy considered as zeta potential. Let us discuss what is surface potential region. The potential at the surface of the solid particle is considered as surface potential region. Next, stern potential region. The strong bonded layer and the millivolts, that is the energy, is consumed very low than the surface potential layer, is considered as sternopotential region. That means the millivolts, this is a unit of zeta potential, by means this indicates the energy. The energy which is consumed very low than the surface potential layer. This phenomenon is known as sternopotential region. Now we have a zeta potential region. The region, the millivolts, is consumed very low compared with the other layers like surface and sternopotential region. This is known as zeta potential region. So here you need to understand one thing, that at this surface potential region we have only surface charge. Which charge we have? Negative charge. This negative charge will combine with positively charged. Okay, so during this, when the negative charge is associated with the positive charge, there will be producing some energy, and the energy consumption of the particular energy in millivolts is very less, and that region is known as sternopotential region. And after some time, the negative charged particles will associated with the positively charged particles, and consumption of the energy again very low compared with other layer like surface and stern, other layer like this stern layer and the surface layer. That means strongly bonded layer and loosely bonded layer energies. Okay, and that consumption of energy is known as zeta potential region. This happens because as the distance increases, the consumption of the energy, that is in millivolts, will be decreases to settle a suspended particle. As the distance increases from the strong bonded layer, the potential will be decreases. That means as the distance is increasing, we discussed in the diagram, so from the negative positive, positive to negative, again negative to positive, again positive to negative. So from this distance, from this negative charge, positive, negative, positive, negative, positive, negative. That means the distance is increasing. That is what the statement. As the distance increases from the strongly bonded, this will be the strongly bonded layer. From this strongly bonded layer, the distance is increases, and the potential will be decreases. Potential means what? The energy will be decreases. This will be the conclusion of the zeta potential. Zeta potential can also calculated by using theoretical models and experimentally determined by calculating zeta potential from the electrophoretic mobility process. This electrophoretic mobility was developed by Marian Smoluchowski in the year 1903. According to this electrophoretic mobility, the equation, that is zeta potential, is equals to summation Rs into summation 0 divided by eta, where summation Rs indicates the relative permeability of electrolyte of the solution, summation naught that indicates the electrical permeativity of the vacuum. This is the zeta indicated by this symbol zeta potential, and eta indicates the viscosity of colloidal system. This is about the zeta potential in detail. And dear student, this zeta potential is very important for your SEM exams. And next I will discuss about the DLVO theory. DLVO means we have 4 different scientists are there. Based on their different names, this theory has been proposed. D stands for Derjaguin. Derjaguin's full name is Boris Derjaguin, and this Derjaguin theory was proposed in the year 1941. Second, L stands for Landau. This Landau's full form is Lev Landau. This also proposed in the year 1941. V stands for Verwey. This Verwey's full form, full name is Evert Verwey, and this was proposed in the year 1948. And last one, O stands for Overbeek. Thunder Overbeek, the full name, and it also proposed in the year 1948. So to remember, this DLVO theory was proposed in the early 1940s by 4 members. Those 4 members are Derjaguin, Landau, Verwey and Overbeek. And this full names, to remembering this full name is also important for your competitive exams with the years. Coming to the statement of the DLVO, that states the distance between 2 dispersed particles mainly influences the particle-particle interactions. Similarly, the distance between 2 dispersed particles, when we have some distance in between 2 dispersed particles, that influences the particle-particle interaction. Or we have another statement that DLVO states that the potential difference and distance among the particles of dispersed phase. That means differences in the potential means there will be requirement of different energy to bring or to decrease the distance among the particles of dispersed phase. This also known as the DLVO statement. Mainly, DLVO explains about the stability of all biphasic systems like colloids, suspensions and emulsions. To understand this DLVO theory in detail, we need to consider 4 cases in detail. In that 4 cases, the first case, that is bringing the same charge particles together. We need to consider the bringing the same charge particle. So obviously what will happen when we are trying to bring the same charged? That means we have taken positive and positively charged. Will they attract or repulse? Obviously repulse each other. they won't come together and they cannot form a flocculation, or they cannot form a precipitation. Okay, so let us discuss according to this DLVO theory what happens when we are trying to bring the same charged particles together, that is case 1. And in case 2, what we are doing here, bringing the opposite charge particles together. Yes, so when we have positively charged and negatively charged particle, what happens? They will get attracts each other, and they can form a coagulation or precipitation, and we will discuss in detail what will happens in the case 2 and case 1. And in case 3, we need to apply, we need to bring forcefully the same charged particles together. So here you need to see the difference between case 1 and case 2. So in case 1, we are just trying, we are not applying any force, but in case 3, forcefully bringing, we are bringing the same charged particles forcefully. Forcefully means what? We need some external energy. And let us see what will happen when we are trying to bring this same charged particles together by applying some extra energy. And in case of 4, here we are just adding limited electrolytes, limited amount of electrolytes in same charged particles. These are the 4 different cases to understand the DLVO theory in detail. And most important thing is you need to remember these case studies, these cases. First one, bring the same charged particles together without adding any energy. In brackets you can consider as without adding energy. In case 2, bringing the opposite charged particles together. Yes, that is very simple. When we are trying to bring the opposite particles, they will get attracted and they will form some coagulated particles or precipitations. In case 3, what we are doing, we are applying some force to bring together. And in case 4, we are just adding the electrolytes to the same charge particles. To understand these 4 cases, let us represent these 4 cases in a graphical manner. So here we can take x-axis, y-axis. In x-axis and y-axis, we need to divide this x and y-axis into 2 portions, that is positive portion and negative portion. This is minus y-axis and this is x-axis, y-axis, and this is positive x, this region is negative x. So on y-axis, we need to take the potential energy on y-axis. On x-axis, we need to take the distance. And in case 1, when we are trying to bring the same charged particles together, so according to this concept, DLVO concept, we will get this curve. We will get this curve, and this curve indicates the case 1. And what happens at case 1? Repulsion will be takes place. Why repulsion is taking place? Because as we know, when we are adding trying to add 2 same particles, then will they attract or will they repulse? Yes, obviously they will repulse each other. That is shown in this graph, and this graph indicates the case 1. And in the second case, what we are doing in second case, we are trying to bring 2 opposite charged particles. Let us take positive and negative. Obviously what happens? The attraction force or attraction in between this positive charge and negative charge will be takes place, and this case 2 will be represented as this curve. This is case 2, also known as attraction, that is VA. And in third case, what happens in third case? What we are doing, we are bringing forcefully to same particles, same charged particles, and that will be indicated by this curve. And here this indicates case 3, and in this case 3 we can see the primary minimum. Primary minimum means the starting point of the same charged particles. Initially, they won't accept, by means they won't be able to attract each other because they are same charged particles, and at some point we can get repulsion potential maximum. Yes, when we are trying to bring, by applying some extra energy to the two same particles, same charged particles, they obviously repulse each other, and this peak point indicates repulsion potential maximum. So potential means what? Energy. There will be the potential energy which is repulsion, which is repulse. That means the hating force will be more. Hating force will be more, and we are keep on continuously applying the force. Then what will happens? Finally, they get penetrates each other, and they will be starts attracting each other. And here this is important curve. At this point we will getting maximum repulsion force, and we are applying the continuous force, and at the last point here they will start attracts each other. And coming to the case 4, this curve indicates the case 4. In case 4, what we are doing? We are just adding limited amount of electrolytes to same charged particles. That means if you take sodium chloride in water, to the same sodium chloride solution, you are just trying to add some extra amount of this sodium chloride. Then what will happen? That will shown in this curve, that is case 4. Here in case 4, we will get a secondary minimum. That means at the initial point, secondary minimum will get. That means here also we will get repulsion forces, and finally they get attracts together. This is the case 4. So these are the 4 different cases of the DLVO concept, and now let us discuss in detail what happens in this each cases in the theoretically. From the graph we get repulsion force that indicated by VR. This represents the case 1. Yes, it is represents the case 1 of DLVO concept, and in this is also known as potential repulsion force, and this can happens when two same charged particles are brought together. This in case of 1. Yes, so this is also known as potential repulsion force. Potential repulsion force. Why it is known as potential repulsion force? Because in case 1, we are trying to bring two same charged particles together, and when these two same charged particles are bringing together, obviously which force will be generated here? Repulsion force will be generated, and that is the reason this also known as potential repulsion force. This mainly depends on the density, surface charge, and thickness of the double layer. This also indicates the magnitude of zeta potential. Yes, this repulsion force is also known as the magnitude of the zeta potential. This point is very important for your competitive exam. Next force we see from the graph, that is attraction force, VA. So this attraction force will be happens in case 2 of DLVO. So what we did in case 2, we just tried to bring two oppositely charged particles we are trying to bring together. So obviously when we have two oppositely charged particles, which force will be takes place here? Attraction force will be takes place. This attraction force in case 2 indicated by VA. This happens when two opposite charged particles brought together, and this may depends on the chemical nature and size of the particle. This is completely depends on the chemical nature, because chemical nature they will be containing positively charged and negatively charged. When we have positive and negatively charged, then only the attraction force will be increases. Repulsive potential maximum. Here this can be understood in the case 3 of DLVO concept, and this happens when two same charge particles were brought too close forcefully. Yes, we did in this case 3. We can observe in the graph also. Initially they will repulse each other, but if you are continuing applying the potential energy to bring together, at the same point they start attracting each other. At initially what happens, say let us take here, these are the two same charged particles. These are the two same charged particles like this. These all are the positively charged particles, and we are bringing to close together. What happens now? Which force will be more? Repulsion force will be more. But to remove this repulsion force, what we are doing? We are adding energy. We are adding the energy. Again, initially they will shows the repulsion. And if you are continuously adding the energy, then at the fine day they will penetrate each other like this. They will be penetrates each other, and then the size of the particle will be increases and density of the particular particle will be increases. This will happens at the repulsion potential maximum. Primary minimum. In this, when two same charged particles bringing together forcefully, the orbital overlaps each other and penetrates each other. This condition is called as primary minimum. We can see in the graph. So initially, just now we discussed, initially they will be repulse each other, and at the fine time, by means of we are continuously keep on applying the energy, so that what happens, the orbital gets overlaps and they will penetrate each other, and this penetration phenomena will be happens at primary minimum. This condition is known as primary minimum. Secondary minimum. This indicates case 4 of DLVO concept. So in case 4, what we did, we just applied limited amount of the electrolytes to the same charged particles. So in this happens when controlled or limited electrolytes were added to the same charged particles. Initially they starts repulse each other about 1000 to 2000 angstroms. Important one for your competitive exams. They will start repulse at about 1000 to 2000 angstrom. Finally, the particles attracts each other as shown in the graph. So, to conclude this DLVO theory, according to DLVO theory, the colloidal particles coagulates when the kinetic energy is sufficient and the potential energy is barrier Vm. Yes, the colloidal particles coagulates when the kinetic energy is sufficient and the potential energy is a barrier. The coagulation or the precipitation of colloids can be accelerated by reducing the height of the potential barrier. So how we can avoid the precipitation of the colloids? By means we can, when we are trying to reduce the height of the potential barrier, and another thing here is by increasing the kinetic energy of the particle. This will be the conclusion of the DLVO theory. Now I will discuss about the applications of DLVO theory. This explains about the stability of some colloidal system and also explains about the adsorption of the biphasic systems like colloids and like suspensions and emulsions. Explains about the particle deposition. This will be the applications of DLVO theory. And in case of the question may ask you explain about DLVO theory in detail, or they may ask you indirect question like explain about the stability of colloids, like this they may ask. Now you need to write about DLVO theory and zeta potential. Don't get confused. Thank you. Hope you understood.
Like, share and subscribe. Hit the bell icon for more updates.